Let's get started. So today we are going to look at chapter 4, section 4.1. So this is about probability and counting rules. So before going to look at those, let's look at the definition of probability. Probability is the mathematical term for the likelihood that something will occur or happen. So the basic idea, the basic concept of the probability is given here. So let's look at two concepts. The first one is the basic concept of probability is the probability experiment. The probability experiment, it is a chance of process that leads to a well-defined some outcomes. What does mean by that? Suppose if you perform some experiment, so the result is going to be our outcome. Okay, an outcome actually is the results of a single experiment or trial, a single trial of the given probability experiment. Okay, so there are some examples I have given here for the probability experiments. Suppose if you toss a coin, of course, you know there are two possibilities we may get. We may get either heads or tails, right? So that is going to be an outcome of the probability experiment, which is tossing a coin, right? Suppose if you roll a die, then what are the possible outcomes we may get? We may get any number, out of six. So if you collect all the possible outcomes for the probability experiment, which is called the sample space. The sample space is nothing but, you're collecting all the results, you know, for the probability experiment. Okay. Suppose look at this, the last example I have given under probability experiment. If you toss two coins, you're tossing two coins, then what are the possibilities or possible outcomes you may get? Well, you may get both of them as heads, or you may have both of them as tails, or you may have the one coin with the heads and another one with tail, or you may get the first coin maybe tail and second one maybe heads. So there are a lot of possibilities, right? So now, if you look at each possibility and putting all under the one set, then that is going to be my sample space for the particular probability experiment. Okay, right. So now look at this example. Finding the sample space for rolling two dice. So now you are rolling two dice. Then how are we going to find the sample space? Remember, sample space means what? You need to collect all the possible outcomes. Okay? So let me draw a picture to find the sample space for this problem. Suppose if I denote x-axis as my first die and denote all the possible outcomes for my second die as a y-axis. That means we know there are 1, 2, 3, 4, 5, 6 possibilities for each die. Okay. So if you plot, points on this xy plane, that is nothing but possible outcomes for all the experiment results, right? So you could just find all the points, all the possible points with these six into six possible values, right? So how many total points you will get here? You will get 6 times 6, right? That is, you should get 36 of them, okay? So there are 36 points. So if you list this thing, um, by using the set notation. So I denote S for the sample space. So I'm writing in set notation. So my sample space is going to be the collection of all the possible outcomes. So I may get, number one from first die and number one from the second die. Or I may get number one from the first one and number two from the second one, right? And so on. So I may get number two from first and number one from the second and number two from the one and number two also from the second and so on. And if you rearrange this order, I will get 36 possibilities, right? So if you rearrange in order, the last outcome may be 6, 6. I'm writing basically all the collections, okay? So you should get 36 outcomes, okay? So if you roll a die, you will get 6 outcomes, but I am rolling now 2 dice, therefore 6 times 6, it should be 36 outcomes. Okay? Okay, so now look at next example. Find a sample space for the gender of the children if a family has 3 children. Use B for boy and G for girl. Okay? Now we are going to look at the, the possible outcomes, for a particular family with 3 children. Okay, suppose say that family has all boys, then the possible outcome is maybe boy, boy, boy. All 3 children are boys, or you may have boy first two maybe boys, and the next one is maybe girl, or maybe first one boy and second one maybe girl and third one maybe boy. In systematic way, if you arrange, you will get all the possible outcomes. So I'm writing in this way. So you may get boy, girl, girl, or you may get girl first, then boy and girl second, or you may get first two girls and boy. So how many are so far? 1, 2, 3, 4, 5, 6, 7. So I need one more. That is all 3 are girls. So this is my possible outcomes. How many outcomes I have? I have 8 outcomes now. Okay. So the number of outcomes is 8. Okay. So you need to make sure that you are writing all the possible ordering for all 3. Okay. Okay. So now we can describe the sample space in terms of the tree diagram. So if you want, you could draw a tree diagram, to find out the sample space. Okay. For example, suppose if you look at, the example 3 here. So if you want, you could draw a tree diagram for this particular problem, 3 children family. How do you make a tree diagram? Tree diagram, you have 2 branches. Uh, so I have, two possible outcomes, maybe girl or boy. Therefore, each branch has 2 possible outcomes. Okay, so this is the possible, first child in the family, maybe girl, maybe boy, we don't know. Now, if you extend 2 more possibilities from each outcome from the first child, then these are the possible outcomes you may get for the for the second child. And I need to extend one more time because we have 3 children family. So from each outcome from the previous branch, you need to extend 2 more possibilities. So this may be girl boy, girl boy, girl boy, or girl boy. So this is going to be my third child. Okay, so this is my third child. This is my first child, second child. This is my first child branches. Okay. So now, since I have a tree diagram, so if you look at carefully, then you can list all the outcomes. Let me change my color here. Okay, so if you look at the first branch, this is nothing but all three are G's. That means what? That means first child may be girl, second one girl, and third one may be girl. So if you look at this branch, this is nothing but first two girls and the third one is boy. So if you look at this branch, that is G, B, G. So if you look at this one, that is girl, boy, boy. So if you look at here, the first branch, that is a boy, girl, girl, and this will be a boy, girl, boy. And the next one, boy, boy, and girl. And the last one is going to be boy, boy, boy. So these are the possible outcomes if you draw a tree diagram. So how many outcomes are here? 1, 2, 3, 4, 5, 6, 7, 8. Yes, there are 8 outcomes. Yes, that is the answer we got earlier. So tree diagram will make easy to list all the possible outcomes. Okay, let's move to the next definition. An event consists of a set of outcomes of the probability experiment. So that means what? Event is kind of a subset of my sample space. Okay, the outcomes you could collect for event from your sample space. So the event may be simple event or maybe compound event. If you have only one outcome, then that is called a simple event. If you have more than one outcome and you are combining them, which is called the compound event. Okay. So, for example, you are rolling a die and getting number 6. Of course, you will get only one outcome, right? So it is considered as a simple event. But if you roll a die, then getting odd number is now you have when you roll a die. What is the possibility of getting odd numbers? Well, there are 3 possibilities now. You may get 1, 3, and 5, right? So in those type of scenario, you may have more than one outcome. So it is called a compound event. Okay, in simple events, you may have only one outcome. In compound events, you may have more than one outcome. Okay. Now, next one, equally likely events. What does it mean by equally likely events? Equally likely events are the events that have the same probability of occurring, right? What does it mean by that? That means, for example, look at this. When you roll a die, what is the chance of getting, say, number 6? What is the chance of getting, say, number 2? Remember, when you roll a die, getting number 6, of course, you will have only one outcome out of 6. Getting number 2 again, you have only one outcome. So the possibility of having outcomes, the number of outcomes are same for both. So if you have kind of situation, so all the events have same number of outcomes, then this is called equally likely events. Okay, so that should have same number of possible outcomes. Okay, look at this note 3. There are three basic interpretations of the probability. There are three types of probabilities available. The first one is called the classical probability. The second one is empirical or relative frequency probability, and third one is subjective probability. So we will look at one by one. Okay. For the classical probability, we use the formula to find the probability of event E. So I'm going to use uppercase letter for events. Okay. So the definition says what? The probability of any event E is given by the number of outcomes in that particular event divided by the total number of outcomes in the sample space. So basically, you are collecting all the possible outcomes for that probability experiment. That is my sample space. In that sample space, now you have to look for the outcomes coming from where? Coming from your particular event. Okay, so look at your event and find possible outcomes. That outcomes would be, coming from your sample space. Okay, so now if you find the ratio of these two possible number of outcomes, which is called the probability of that event. Okay, so in notation wise, we could use P of E as the probability of event E, that is given by little n of E over little n of S. So here E stands for the particular event and S stands for the sample space. Okay, so where NE is the number of outcomes in your event E and NS is the number of outcomes in the sample space S. Okay, so now let's look at that example 4. Find the probability of getting a black 6 when one card is randomly selected from an ordinary deck of cards. Remember, in ordinary deck, we have 52 cards, right? In 52 cards, there are 26 black and 26 red. Remember, among those 26 blacks, we have 13, which is called spade, and 13 clubs. In red cards, there are 13 of, we call that as hearts, and 13 diamonds. Okay, so if you are not familiar about the card pack, and you can just go and Google it. There are a lot of videos you will find out, about the ordinary card packs. Okay, so in this case, you are drawing only a single card, but you need to get number 6. Okay, so remember, from each suit, there are 4 suits. This is called the number of suits. So there are 4 suits in total. For each suit, you will have 13 of them, right? So you see the number 2, 3, 4, 5, 6, 7, 8, 9, 10, and you will see one card with ace, and you will see with the king, you see with queen, and you will see with jack. So if you count, you should get 13 in total, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. For each suit, you will have this much number of cards. Okay? So the question is now, what is the probability of getting a black 6? Remember, there are 26 blacks. Among those 26, for each suit, there are 13 of them. For each 13, there is only 1 6, right? Therefore, in both spades and clubs, we will have together 2 6. Okay, So there are two six. So if you want, you could denote your event E as uh, getting black. So this is my event E. So they're asking us to find the probability of getting that event. Therefore, the probability of getting E formula says that is nothing but NE over NS, the number of possible outcomes in event E. My event E is, remember, getting a black 6. So there are two of them, one from spade and one from club. So there are two out of the number of total, the outcomes in your sample space. Remember, sample space is the collection of all the possible outcomes. If you are given 52 cards, you are drawing single card. So what is the probability of getting that is a black? Well, there are 2 out of 52, right? So my sample space consists of all the cards. There are 52 of them. Therefore, answer is 2 over 52. So if you want, you could simplify, and I'm leaving my answer as a fraction. Unless they ask you to do, you could keep all these your answer in fraction rather than writing in decimal, okay? Okay, let's look at example 5. If a family has 3 children, find the probability that exactly 2 of the 3 children are boys. Remember, we already have seen about this problem in the previous example. So we already have the sample space for a 3 children family, right? Let me go back and check there. So we did here the possible outcomes for 3 children family, right? So my sample space S was here the collection of all 8 possible outcomes. So this is my sample space. There are 8 of them. So the little n of S is 8 here. Okay. The question is, what's that? Find the probability that exactly 2 of the 3 children are boys. So we are looking for 2 boys among 3 children, right? Therefore, my event E is here, having 2 boys in that family, 3 children family. Okay, the probability of, right, having exactly 2 boys, that is my event E now. Formula says that is n of E over n of S. Remember, E is now getting 2 boys. So now ask yourself, in your sample space, how many possible outcomes do you have with 2 boys? In another word, with 2 Bs. So if you go back and check your sample space, there, how many outcomes do you have among, in that 8 outcomes, how many of them are with two boys, 2 Bs? So that means this is one of them, 2 Bs I have out of 3. This is another one. This is the third one. So I have 3 possible outcomes out of 8, right? Those who have, 2 Bs. Therefore, my possible outcomes for getting 2 boys is 3 over n of S. The possible outcomes in my sample space, remember sample space is the collection of all possible outcomes. So now my possible outcomes in sample space is 8. Therefore, the answer is 3 over 8. I'm leaving as it is. Okay. Remember, in all the probability questions, only thing is the understanding. You need to put correct numbers in the in the fraction. You need to put the correct place. Okay, so you ask yourself, first of all, you need to define any event. Then you need to ask yourself about your sample space. Then check how many outcomes there in your sample space. Then you have to look for the number of outcomes in that sample space which are coming from your event E. Then you need to take the ratios of n of E and n of S, and you will get the probability. Now look at next one. A card is drawn from an ordinary deck. Find the probability of getting a heart. Remember, you are drawing a single card. Okay, so I explained already here about the ordinary card pack. So getting hurt, remember there are 13 of them. So there are 13 possibilities out of 52. Getting black, there are 26 black out of 56. Okay, the 8 diamonds. So how many possibilities you will have out of 52, which is 8 and diamond? Well, you have only one such a card. Queen. For each suit, you have one queen. So I have 4 of them. 4 suits are there. Spades, clubs, hearts, and diamonds. For each suit, you will have one queen, and therefore 4 of them. It is 4. But remember, you need to put the number of sample space outcomes in the denominator, always 52, right? So the next one, the last one, the face card. Remember, these 3 are the face card we have in the card pack: king, queen, and jack. For each suit, there are 3 face cards, but I have 4 of them. Therefore, 4 times 3, so which is 12. The 12 of face cards in total out of 52. So there are 12 out of 52. Remember, for all the problems here, I'm using my probability formula, which is given by NE over NS. I'm just directly writing my answer, NE over NS as here. Okay, so the denominator of each fraction is nothing but N of E, and the denominator is N of S, and the numerator is N of E. Okay, so simply just count how many outcomes for each event. That's it. Okay, now let's look at the probability rules or properties. So these are the, if you think of, the probability rules. What are those? The first one, the probability of any event E, that is be denoted by P of E. The probability of any event E is just a number, or you could write in either fraction or decimal. That number is always between 0 and 1, including 0 and 1. Okay, this is denoted by in inequality form. This is the inequality. So my probability of any event E is always bounded by 0 and 1. 0 and 1 are included in my inequality. That is why I have equal sign here. That means what? That means your probability answer may be 0, maybe maximum 1, or in most of the cases, your probability answer will be between 0 and 1. The second one says the sum of the probability of all the outcomes in the sample space is 1. If you add all the possible outcomes, the probability of all the possible outcomes is always 1. That means what? In notation wise, the probability of all the outcomes means we denote by sample space S, right? That means the probability of sample space is always going to be 1. Okay, I need to tell one thing here. Any event E is always going to be a subset of the sample space. So this notation we use, in set notation we use for subset. Subset is kind of the smaller event compared to the larger event sample space S. Sample space S is kind of a big guy, having all the collection of your outcomes. But an event is basically we are choosing an outcome from your sample space, right? That is why we call E as subset of S. Okay. If an event E cannot occur, that means what? If it is not possible to, have that event E, then that probability is always 0. So the probability of impossible event is always 0, in other words. So impossible event, we denote by this notation. So we call this as an empty set. Okay. So the impossible event is always going to be empty set. The probability of impossible event is always 0. Okay. So in notation wise, the probability of empty set is always 0. If an event E is, for certain, for sure, for 100%, you are sure that that event is going to happen. Those kind of event has the probability of maximum 1. So the probability of any certain event is always 1. So you know 100% sure that that event is going to happen, right? It is a certain event. So the probability of certain event is always going to be 1. So these are the things we have under probability. So let me summarize here. The probability of any event E is always bounded by 0 and 1. The probability of sample space is always 1. The probability of empty or impossible event is always 0. The probability of certain event, suppose if you know any certain event going to happen for sure, so always going to be 1. Okay, that is there. Now next question is, when a single die is rolled, find the probability of the following events. Part A says that the given event, now E, this is my event E, right? Or experiment. What is the probability of getting number 7? Remember, when you roll a die, there is no way to get number 7, right? Maximum you have 6. So that means what? That means this event is not going to happen. This is impossible event, right? When you roll a die. Therefore, this is impossible event. So my event E is now empty now, right? It is always going to be 0. The probability answer is 0. Part B, getting a number less than 5. Okay, remember, if you write down the sample space for this problem, which problem? When you roll a single die, there are 6 possibilities you may get. You may get any number out of these 6, right? We don't know which one you are going to get. For sure, I know I will get any of these 6 numbers, one of these 6 numbers. So now my event E is getting a number which is less than 5. Now this is the particular event they are asking us to find the probability. That is the event E for this. Okay, so if you look at your sample space here, how many possible outcomes I have? Remember, my event E is what now? The number which is less than 5. So if you look at your sample space, yes, there are 4 possibilities, right? These are the 4 numbers which are less than 5. So you may get any of these out of 4. Therefore, the probability of getting number less than 5, I am denoting that event as E. So the probability of that E is going to be, formula says that is N of E over N of S. Okay. The number of possible outcomes in your event E, my event E is getting number less than 5. So there are 4 possibilities, 4 outcomes out of N of S is my sample space. Sample space has in total, sample space has 1, 2, 3, 4, 5, 6. Therefore, there are 6 outcomes in my sample space. Out of 6, there are 4 possibilities of getting number which is less than 5. So my answer is 4 over 6. If you want, you could simplify this. This is 2/3. Let's look at next definition then. The complement of any event E is the set of outcomes in the sample space that are not in your event E. So basically, the complement of any event is basically, you are collecting all the outcomes which are not in that event E, but that is in my sample space. So that is denoted by E bar. So we have to read like E bar. So E bar is nothing but the complement event of any event E. Okay? So remember, whenever you are asked to, find the probability, first of all, you have to ask yourself, where's my sample space? What are the outcomes I have in my sample space? Ask yourself. Collect all the information from your sample space. Then you have to look for your event E. So event E is basically you are collecting the outcomes from event E from where? From your sample space. Okay? Sample space is always, going to be a key when you do the problem. Okay, so now there are some rules or properties we have for the complement event. In another word, what is the relationship between any event E and its complement event E bar? These are the three possible relationships we have. Okay, so let me write down those three. The probability of the complement of any event E, that is P of E bar, that is given by nothing but 1 minus P of that event E. Or if you want to find the probability of any event E, that is simply you have to subtract the probability of E bar from 1. Or the third relationship says the probability of any event E plus the probability of the complements of that event E is always adding up to 1. Okay, remember these all three, the relationship are equivalent, right? Suppose if you know one relationship, from there you could derive the second one, right? All three have sort of similar explanation, right? But the way I'm writing is different. Okay, so keep in mind all three possible relationship between E bar and E. Okay, the next note, what is that note? The probabilities can be represented pictorially or by using the diagram. So let us write down then that, right? So let me explain that. When diagram is nothing but with the box, this box denoted as my sample space. Collection of all the outcomes will be inside this box. Suppose my event is here. Remember, as I said earlier, event E is always going to be the inside of your sample space. Sample space is kind of big guy. So this is my event. The probability of, suppose if my probability of E is, say, let me use some different color. Suppose if my probability of E is here, then my probability of E bar should be outside of E. So if you add your probability E and your probability E bar, then you will come up with the total probability. That is my, the probability of sample space. Okay, so that is, you should get 1. So this is the picture I could, explain my the relationship between my given event E and its complement. Okay, let's look at this problem. In a study, it was found that 24% of people who were victims of a violent crime were aged between 20 to 24. If a person is selected at random, find the probability that the person is younger than 20 or older than 24. Okay. Now, if you look at carefully, right, the given probability, there are 24 chance of having the people committed crime was the age between 20 to 24, right? Suppose if my event E is the people, those who have age 20 to 24, then of course the event E bar is, as I said earlier, should be complement of this event outside of this event, right? In other words, negation of this event. So the question is now what? Find the probability that the person is younger than 20 or older than 24. That is basically not in this range, right? Out of this range. So that is going to be my event E complement. If your event E is between 20 to 24, then your event E bar is outside of this range. That means basically it should be younger than 20 or older than 24, right? So basically they are asking us to find the probability of event E bar. So this is my event E bar, right? If my event E is age from 20 to 24, then my event E bar is, the negation of that, outside of that event. So it's going to be outside of that range, technically speaking. So it's going to be less than 20 or older than 24. So in notation wise, if you want to find the probability of that event, that is nothing but the probability of E complement, right? If you look at the previous relationship between E complement and E, remember we have three, properties of E complement. The probability of any event complement is given by 1 minus of probability of that event, right? Now, if my event E is the age 20 to 24, then what is the probability of, having that age range? It is given in the problem. Of course, there are 24 people out of 100, if you say. That means the chance of getting this event is 24 percentage, right? That is nothing but 0.24. Okay, so 24 percentage means 24 out of 100. So if you simplify this is nothing but 0.24. Okay, therefore the probability of E complement is nothing but 1 minus PE. PE is 0.24, so subtract from 1, so you will get the remaining from 1, which is the given, the E complement. So that is my answer. So read your problem carefully, identify event E and E bar, then use the formula whatever you have. Okay, read the problem carefully, identify the event E and E bar, then use the relationship whatever we have, then you will get the answer. Okay, so this is all about the classical probability. Now the second probability, the formula we have for the empirical probability. Empirical probability is always dealing with what? Dealing with the frequencies. Okay, suppose if you know the frequencies, right, for the given particular event, then we use the empirical probability formula. The given frequency distributions, the probability of an event E, right, uh, being in a given class is given by the probability of E, that is, look at the particular class frequency, then divide by the total number of, outcomes, that is basically my total number of frequencies. We all are familiar with this notation, right? Little f and little n. Remember when you study there under frequency distribution table, we had those two notations, right? So little f here is number of outcomes in that event, and little n is the total outcome. So read the probability problem carefully and identify and ask yourself where is f and n. Then simply you plugging those values into this formula to find, the empirical probability. Okay, we will look at one example. Okay, look at this problem. So in a sample of 50 people, 21 had type O blood, 22 had type A blood, 5 had type B blood, and 2 had type AB. Set up a frequency distribution table, then find the following probabilities. So first of all, let us find out the frequency distribution table for this problem. Okay, so I'm going to make a table. Okay, so now this is blood type. This is corresponding frequency. Okay, what are the possible types we have? We have type O blood, A, B, and AB. Okay, so now for each corresponding type, we look at how many people are there. For type O, there are 22, not 21, right? 21 had type O. So 21 type O, and 22 type A, and 5 had type B, and 2 had type AB. When you add all the frequency values along that column, that is nothing but my little n, right? We go and check our frequency distribution table problem. So the little n is nothing but the sum of my frequencies, my sum of frequency. They are telling that we have 50 people in total. That means if we add all frequency possible values, you should get 50. 21 plus 22, 43. 43 plus 5 is 48. 48 plus 2 is 50. Yes, we are getting correctly. So my total number of outcomes is now 50. There are 50 possible persons. Okay. Here, each type blood is going to be my particular event, right? So there are 4 different events. Now, my sample space is what? Collection of all type bloods. O, A, B, and AB. Okay. So that is there. So my event sample space for this problem is collection of all the type bloods. That is O, A, B, and B, right? So now let's find out the probability. Actually, the question is what? Question is finding the following probability. So you need to find the probability for each problem here. So for part A, what is the probability of the choose person has type O blood? So this is going to be my particular event for type or for the problem number 1. Okay, so we need to find the probability of those who have type O. We are choosing a person out of 50. What is the chance of having that person, with type O blood? So formula says that what? So now this is going to be my event E. So remember, I have now frequency distribution table. Therefore, I'm going to use my empirical probability formula. The probability of any event E is given by the corresponding frequency divided by total n, right? A total value of your outcome. So I'm looking for now type O. Type O is my first class, right? So that is my F here. So F is now 21 for type O. Divide by what? N. So basically I'm using the formula P of E, which is a little f over little n. For little f for this particular type O is 21 over n is 50. So if you want, you could simplify and write it down in decimal place. I'm leaving as it is. Part B, person as a type A or type B. Oh, now you need to check 2 possibilities, right? Type A or type B. So look at for the both possibilities. Type A has a 22 frequency. Type B has 5 in frequency. Add them and find the total possibilities. So which is 22 plus 5, right? Over my total outcome is always going to be 52. Sorry, 50. So that is going to be 27 over 50. Part C. a person you are choosing neither type A nor type O. So you have to exclude now these two. Okay? So the probability of neither A nor type O. So that means among this class now you need to exclude these two, right? Type A and type O. I don't want A and O. You take the remaining B and AB. Okay? So B and AB is going to be 5 and 2. So simply add them out of 50. That is 7 over 50. And the last one, the probability of a person does not have type AB. Does not have type AB. Right? Suppose if my event E is having type E, then does not have E is nothing but my E bar, right? So that means they are asking us to find the probability of does not, have type AB. That means they are asking basically the probability of E bar, right? So that is basically 1 minus the probability of E, right? So let me write down that in separate way, otherwise, right? Whereas my event E is have type AB. If my event E, those who have type AB, then my event E prime means it does not have that, the negation, the complement of that event. Okay, how do I find that? Okay, the probability of E bar is 1 minus probability of E, whereas my E is having type AB, right? Okay, what is my type AB? Type AB has a 2 out of 50. So first find the probability of this event. So I'm using a foreign formula for first this event. That means the probability of having type AB, right? The frequency for type AB is 2. So that is 2. F is 2. And N is always 50. Therefore, 2 over 50 for this piece. Then I'm subtracting from 1. Then you will get the complement of that event. So if you simplify this, you should get 50 minus 2, which is 48 over 50. If you want, you could simplify this. If you divide by 2, you get 24 out of 25. So these are the basic probabilities, okay? So make sure that you understand the concept and the formula. Let's move to the last type of probability, that is the subjective probability. Subjective probability is kind of, the individual probability. That means that depends person to person based on the past experience. Uh, the, the individual can find the probability. Those kind of probabilities are called the subjective probability. There's no formal calculations for that. That is purely based on their experience, right? So it differs from person to person, subjective probabilities. So we are not going to do in detail about the subjective probabilities in this